the details of this formula. You just know we measure the distance along each aspect and then sum them up based on the user's preference. We have talked about the different feature types. We have talked about how do we use those feature types. Here is how do we construct those feature types. It's a very standard way of doing that. Basically, it's a classification process. We select the most promising audio features, do a feature selection, use a special SVM algorithm to classify them. And then after classification, we will have different feature types describing different aspects. For those which are not related to class-based aspects, we just use the we just use the music values as a feature vector. Here we have some technical contributions like the ePicasso SVM. Picasso here, I just want to highlight, is a very special SVM learning algorithm. It has a very good property, which is its running time is inversely dependent on the size of the training data size. So which means you give it more data for training, the faster it can train. The assumption is that the generalization performance is the same. So the original Picasso algorithm is for binary classification. We just did some simple extension from binary to multi-class classification. So, but in the Picasso algorithm in general, I'd like to encourage you to read more about it. It's very interesting. Okay, after we constructed all the feature values from the either query or the music database, we need to have an indexing module to index all those feature vectors. The basic idea is to index each feature type separately by using their most suitable algorithm. So it's called a hybrid structure. For document vector, we use the popular inverted list to index that from text information retrieval field. For those real vectors, we use LSH based. Here in the querying phase, we actually use the original locality sensitive hashing algorithm. But in the indexing phase, in the phase of constructing the index, we did some improvement, which is to allow the incremental indexing. Because in the commercial application, every day user uploads new videos. So once you upload, let's say, 1,000 new videos, you don't need to re-index the whole database again. You just add the new videos into the existing index. So we call that incremental indexing. Yeah. I won't talk about the details, just show you the idea. Last is the quantity ranking. It's essentially the implementation of the personalized music similarity measure. Here, I'd like to highlight, once the user chose some of their preferred music dimensions, the personalized similarity measure is accumulative in nature, which means the music items in the database, if they are closer, if they are near to the query, in more music classes, they are more likely to rank top in the final retrieval results. So in this case, the top returned music items will be those that satisfy most of those customized dimensions. Yeah, that makes sense, right? Here is the implementation of the personalization functionality. This is the prototype of our search. We evaluated our similarity measure in a search engine. This is a prototype of that search engine. We allow text query and audio query input. And based on that, we allow users to customize different music dimensions, but it's not very clear. This is text, genre, mood, instrument, vocal, and tempo. So they may choose different aspects to search similar music to those queries. I'll show you a demo later on. If you have any questions, feel free to ask me. Okay, now you have a rough structure, a rough idea about the framework. I will talk about the evaluation part. Do you have any questions about the framework? Okay. Because during the time we evaluated our system, we focused on real-life data, which means we So we crawled all the music data from YouTube. No matter, you all know the audio quality on YouTube is not very good, but we really want to see the performance of our system on those real life data. We have two test collections. One is 3K with human annotation. The purpose is to train the system and evaluate the performance on smaller data sets. And the second collection is about 100K music data without human annotation. And we also designed some queries with different number of personalized dimensions to reflect the user's needs. They may want to personalize one dimension or one aspect, or they may want to personalize more. We have 24 subjects, 10 are amateur musicians and 14 are music hobbyists, just like most of us. We don't know much about the music terminology, but we just like music, want to search more our preferred music. And procedure is that for either the low or high complex queries, here we mean in either the music query with only one music aspects personalized or with more, we do the following. We ask the volunteer to randomly choose a query with the personalized facet to do the search. And after that, the volunteer is asked to judge the relevance of the top 30 returned results. If the result is relevant in any of the personalized dimensions, we say it's relevant. And later on we use that to calculate the precision at n as the evaluation method. And we also build two baseline methods, which is the raw audio features and also the other raw audio feature processed by PCA, principal component analysis, to reduce the dimensionality. Here are some results. We'll only show you the final results. For the results of each component, they're all written in the paper or at the end of the talk. So if you are interested, we can talk about that later. Here is the final effectiveness result on the small collection with low complex queries. We can see that the new feature type we proposed generally gives us better precision in the retrieval results. Yeah, for the audio features and audio feature PC, generally they perform not as good as the proposed one. The main reason is that because our feature describes different aspects using different music class or classification results, that means our feature type can more effectively distinguish between different music dimensions. In contrast, for audio features or audio features PCA, they cannot distinguish between different audio aspects. They just use the same set of features to describe whatever music aspect. So on top of that, no matter what personalization you do, you will not get the actual personalized result. Here is another set with high complex queries. The same performance was observed. And this is on the large database. On the large test collection, we didn't do the comparison. We just tested the validity of the new features, whether it will give us a reasonable performance. From these two figures, we can see that performance is reasonable. Yeah, which means for each search operation, the user can get a meaningful amount of relevant results. About the efficiency, we tested the indexing module separately. We tested the classification module separately. And here, I just want to show you the overall performance, which is once you upload a query, do a search, how fast the system will retain the results. When the database passes 100K, those two columns actually are simulation results. At a scale of 1 million sounds in the database, the system response time is around 1.7 seconds. Yeah, 1.7 seconds. So it's generally affordable in commercial application scenario. Okay, now we come to the conclusion part. So basically propose a framework which allows user to adaptively measure similarity measure. And we can also use